Hey class, this is Dr. Martino again. This is PV Loop video number 2. So in the last video, we talked about most of the basics. I want to add several key pieces to the basics that I didn't have time for last time and then move on to example problems. So the first one that I would like to bring up is stroke volume. Stroke volume is the amount of fluid, in this case blood, that is ejected from a chamber, in this case the left ventricle, per stroke. It's called the stroke volume. Okay, that is the difference between end diastolic volume and end systolic volume, which in this example ends up being about 65 mils of blood. Okay, 65 mils of blood. In addition, we also have the area under this curve, and that represents something called stroke work. So we can calculate the amount of work done by the left chamber of the heart. If we extend this further, then we can calculate the total oxygen consumption for the left ventricle per beat. Okay, let's move on to an example. So this is a generic, normal left ventricular PV loop that you can use for lots of practice. Okay, so in this particular example, we're going to use something called an increase in preload. So first, let's define the preload. Preload is the amount, it's the amount of fluid, right? It's the amount of fluid that's in the chamber before contraction begins. So that's all that is. So in a normal standard curve, the way we're defining it, the preload would be the difference between the end diastolic and end systolic, which in this case happens to be about 65 mils of blood. Okay, 65 mils of blood. So what we're saying here is we want, and what happens if you increase preload, right? What if it increases? So you start all of these problems from the same place. You start them from this point here, which is end systolic volume, which in this case happens to be about 75 mils. All right. It is, you rarely eject all of the blood from the heart under normal circumstances. So you normally have a small amount, somewhere between 50 and 75 mils, that's remaining in any of the chambers at any given point. Okay, so we have to say to ourselves, where are we starting from? So this is a normal curve. We want to increase preload. So what is preload? Preload is the amount of blood in the chamber. So what we say is we start from here, and the first question we're going to ask ourselves is there an increase or decrease in preload? So you get to the point where you started, and you say, is it less than that end diastolic volume, or is it greater than that? Well, if it's increasing the preload, the point of end diastolic volume must be somewhere further up in the curve. Okay, so let's just say, for instance, that this ends up being 160 mils. Okay, 160 mils. Okay, sorry about that. So, all right, so let's go back. Let's say it's about 160 mils. So the first question you're going to ask yourself on any PV loop is you're going to start in the end systolic volume, right, where there's almost no pressure. You're going to go up the diastolic curve, and there's either going to be an increase, in this case an increase, or a decrease in the preload. Preload's the amount of blood in the heart. If it's decrease, the amount will stay somewhere over here. If it's an increase, in this case it's generic, it'll be somewhere on this side. Okay, now once you've gotten that new point of end diastolic volume, then you're going to start isovolumic contraction. You're going to get to this point here, which is the general point at where the aortic valve normally opens. The next question you will ask yourself is, did anything change? Do we have any information that the back pressure, the afterload on the aortic valve has changed, increased or decreased? And the answer is no. So it's going to open up at roughly the same pressure. So then what we're going to do is we're going to have an ejection. And we're going to come right back to here and right back down. So as you can see, an increase in preload, right, gives us an overall larger PV loop. Nothing else has changed, right? The diastolic curve hasn't shifted this way or this way. The systolic curve hasn't shifted this way or this way, right? The point at where the aortic valve opens has not changed. The point at where the aortic valve closes has not changed. So all you have is more blood comes in and more blood comes out. So this can be explained by something called the Frank-Starling law of the heart. And the Frank-Starling law of the heart, and Frank and Starling were two different people, by the way, researchers in early cardiovascular research, states that in layman's terms, what comes in must go out. So if you bring in more fluid has to go out and everything resets. The reason that happens is because of an additional piece of information, that there's a greater overlap in the myosin and actin when there's more blood in the chamber. There's a greater stretch on the heart. Now, something I haven't mentioned yet, but you got to go back to skeletal muscle, and this is why everything in physiology builds and everything else, and that the resting length, if you remember resting length in skeletal muscles when we were using the bicep example, resting length and optimal length are exactly the same position. Okay, resting length and optimal length are exactly the same position. But in the heart, the resting length of the normal heart chambers is below optimal. Okay, there's a disconnect between the resting length and the optimal length. So when more blood comes into any of the chambers, they expand, right? So right now you can imagine that those chambers and the actin and myosin are a little bit more compressed than they should be. They're crunched up. As you expand the chamber by increasing the volume, you're going to get more optimal overlap between actin and myosin, which means you can form more cross bridges, which means that you can produce more force. And in fact, you actually get more force, right? There's additional force that's produced, and that's represented by this additional area here, and then a higher peak. So that's the Frank-Starling law of the heart, and that's under normal, resting, healthy conditions. This goes all awry when you have a pathological situation. So to review, one, you should use these diagrams in this PowerPoint presentation and the PowerPoint presentations for practice. Two, preload is the amount of fluid that is in the chamber before it begins to contract. Three, you always start all of these after you've drawn them, all of these examples from this point here, and you start moving forward and you start asking yourself questions. Does the preload change? Is it less or is it more? Does the diastolic curve change? Does it go this way? Does it go this way? Is the point at which the aortic valve opens, is it increased or is it decreased? Is the point where the aortic valve closes increased or decreased? And is the systolic curve coming down or is it going up? And you do that with every single question, whether we're talking about the left ventricle or we're talking about the right ventricle or even the atria. So that's the second in a series of example, smaller lectures. It's a little bit longer than 5 to 7 minutes, but hopefully the next few will go shorter. So that's all I got for you now. Have a great day.